Hey folks, welcome to this channel and welcome to this video. I'm Saptarshi Mukherjee. I'm a software engineer 3 at Google. I've been into computer programming for quite a long time and I've held many titles in computer programming. I've also been into development, I've been into hackathons. I've had some time spent in research in edge computing, blockchain. You can see I've been a member of National Blockchain Project and I've done some research in edge computing and some other areas like graph algorithms. So yeah, this is a bit about myself. In this video, I'm going to discuss a very interesting and very important thing for a large category of students who are solving easy problems in computer programming, hard problems in computer programming, and solving basic DSA problems. This is one thing that keeps coming up: dynamic programming. And before that, another thing comes up, which is recursion. If you know recursion well, dynamic programming is just one step away. So this particular session is going to focus on recursion. We are going to see what recursion actually is. We are going to see it slightly closely. And then we will look at DP. We will discuss some very basic topics. That what are the categories of DP, what gets classified as DP, and what is not DP. And then we will look at some examples and try to understand all of these things. And by the end of it, I actually want that we'll be able to solve the dynamic programming problems in the CICS problem set. I had posted one problem and I'm going to post the solutions of other problems as well. We will try to bucket them. We'll try to see what are the similarities across these problems. You'll find some easy problems, some moderate problems, and some really good problems in this problem set. And then when we have solved this problem, we will shift to some harder problems. So this particular session is going to be a prerequisite, very important prerequisite of all the upcoming DP sessions that I'll be trying to upload. So yeah, do watch this session and let me know how you felt about it. So this is one problem with which I'd like to start this discussion: Fibonacci numbers. Fibonacci numbers, this is the series of Fibonacci. This is a Fibonacci series. The series written in green: 0, 1, 1, 2, 3, 5, 8, 13, 21. Now, this is just a series, just like natural numbers. What is the difference, or what is the nature of this series? If you look at any number, it is formed by the sum of the previous two numbers. 2 plus 3 gives me 5. Similarly, I can say 5 plus 8 will give me 13. Similarly, 8 plus 13 gives me 21. And that's from the very beginning. 0 plus 1 will give me 1. 1 plus 1 gives me 2, and so on. Which means that somehow it starts with 0 and 1, and then each number is the sum of the previous two numbers. And now the question is, in such a series, how do you find the nth Fibonacci number? So let us see how to find this. The basic understanding, the basic thing that we know is that the Fibonacci number, the nth Fibonacci number, is basically the summation of n minus 1th Fibonacci number and n minus 2th Fibonacci number. And this is exactly what we try to use, try to exploit in our programming. We say we know this relation. What is this relation? This is a relation of a problem that we want to solve with a similar problem with lesser input. This is a relation which basically tells me that if I know the answers to some smaller problems, fib of n minus 1 and fib of n minus 2, then by a simple addition I can get fib of n. Which means that somewhere my problem can be easily solved if I know the answers to some smaller problems. So these are referred to as smaller problems or sub-problems. Your actual problem is fib of n, and you are saying fib of n minus 1 and fib of n minus 2. If I have them, I can solve my main problem easily. Those are again fib, but on smaller inputs. We call them as sub-problems. And this kind of a relation, which helps in solving your problem by using the solutions to smaller problems, is known as a recurrence relation. This is known as a recurrence relation. Okay, so now how do we solve it? We have a tool for it. Whenever we can express a problem in terms of sub-problems, one programming tool available to us to do it, to implement it, is actually recursion. In recursion, we can say that you are writing a fib function. Call the same fib function from within fib. So basically, we will say from within fib function, you are basically working on fib n, call fib n minus 1. And and after that call fib n minus 2. You will get the responses from them, you add them and you solve them. You then just add and return the answer. That is the idea. Now, how does this actually work? So the idea basically is that fib function is going to call itself. That is recursion. And for recursion, for solving recursion problems, there are a few things that are very necessary. The first thing is you should first assume that what your recursive function is solving. That first thing you have to assume that okay, this is what my recursive function is doing. And you have to assume that okay, the smaller subproblems are going to work. If I call them, they are going to work. You need to ensure that the actual function you are writing is going to work. Assume that the smaller functions are working. You return the right sum. So let us see. If I write a fib function, what is the expectation? That it will take some n and it will return some int. The n can also be of type int. This is C++ or Java syntax or C syntax. So you have a function which takes some number and it has to return the nth Fibonacci number. So now what we say is assume that the smaller problems, if it calls the smaller problems, they will work, and then utilize that to make it work. So what we say is okay, get the smaller numbers. So you have something like this. Let's say something like this. The previous one is fib of n minus 1. This is your previous number. And the one that is before that, P2, the one that is before that, we can call it as fib of n minus 2. We will call them, and their sum will basically return the answer. I mean, their sum will give me the answer to this problem. So I'll assume that they will work correctly. That is my assumption. And then I'll say, okay, now the step comes. I'll basically use them to return the answer. So my answer will be return P1 plus P2. Right? In a one-liner, you can write this entire thing as return fib of n minus 1 plus fib of n minus 2. Now the thing is that, okay, we have assumed that these are working. For which case is this illogical? In which case does this sound illogical? Like if it is n equal to 5, I can say it depends on the previous two. But if my n is at the beginning, 0 and 1, 0 doesn't have two numbers before it. Similarly, 1 doesn't have two numbers before it. I need two numbers before it. So basically, for that I need an exception. That is known as a base case. I basically say that, okay, if my n is less than equal to 1, then I need some base case. If you see, if n is less than equal to 1, n and the number, n and the nth Fibonacci number is the same. So this is an easy way to say, okay, return n. Return n. Okay, now P1 and P2 you can actually replace by these things only. So instead of P1 and P2, you can directly write those things. You can write fib of n minus 1 plus fib of n minus 2. So then the code looks compact. So you are calling two functions in the same line and using their outputs, you are solving your own problem. Now the question is, how does it actually work? We are going to quickly see through a dry run how this actually works. So let us take something like n equal to 3. N equal to 3. So what we have is basically this. We have this code where 3 has been passed. So here basically 3 has been passed. If 3 has been passed, we know that the first line doesn't get satisfied, n less than equal to 1. So this is not executed. What is executed? Fib of n minus 1 and fib of n minus 2. So this guy will basically call these two things. First, it will call the first thing that comes up, left to right. It's left to right execution. So it calls the first thing that comes up. Now, the next part is this same thing now comes up. I'll keep a copy. Yeah. So what you see over here is I'm calling fib of n minus 1, which means the same fib function is getting called. So yes, same fib function is getting called. So let us see, this fib function is getting called with n minus 1, which is 3 minus 1, that is 2. So here the value of n will be 2. Now 2 is less than equal to 1? No, 2 is not less than equal to 1. And so this will also come to this last line, it will call the two things, fib of n minus 1 and fib of n minus 2. Fib of n minus 1 and fib of n minus 2. Fib of n minus 2. Fib of n minus 1 basically will have, here n was 2, so 2 minus 1 will be 1. On the right hand side, 2 minus 2, n minus 2 means 2 minus 2, which is 0. It will be 0. So for 1, it will satisfy this expression, it will return 1, which is the right answer for n equal to 1. So it will return 1 from over here. And this guy will return 0. The execution happens left to right. So first this thing will come after executing, and then this thing will come. Okay, so what comes up basically is first that 1, then this 0, and then you're basically adding it, 1 plus 0, which is equal to 1. You're going to return it. You return this 1 to this fib of n minus 1. Now fib of n minus 1 is known. Now fib of n minus 2 is left. This guy will call fib of n minus 2. And over there also you have a similar thing. Let's track this. So here n is equal to 3 minus 2, that is 1. So you have 1 over here. For 1, this condition is satisfied, which means you will return 1. So from here you return 1. And then this does this thing. So 1 plus 1 is equal to 2. Here you are getting 1, there you are getting 1. So this will basically do 1 plus 1 is equal to 2. So what do we see over here? We had made one very big assumption that our subproblems will work. The subproblems don't magically work. The subproblems will get called and they will keep going deeper. And at the deepest level, your base case will help in returning the right solution for the smallest subproblem. For that, we write the base case, for which we should not depend on subproblems. For that lowest level, we actually have base cases. So we will return the answer from there. Got it? So now basically, what happens is we keep on going deeper. We keep on going deeper, we get the answers. Now, if you visualize for n equal to 4, what happens? At the top, n equal to 4 will come. It will call n equal to 3 and 4 minus 2, that is n equal to 2. So in this way, this will have a similar thing. This will have a similar thing. So this is the way this problem basically gets solved. So what we understood is basically that this is the base case. And this is the main logic, also referred to as the recursive case. Recursive case. All right. Now, stepping down. So this is a basic recurrence relation. In this way, you can visualize a recursive function. You can write a recursive function and you can visualize in this way. So if I visualize a slightly larger version of it, let's say I call fib of 4. What happens? Fib of 4 will call fib of 3. Fib of 3, fib of 4 will call fib of 3 and fib of 2. Fib of 3 will call fib of 2 and fib of 1, n minus 1 and n minus 2. So fib of 2 and fib of 1. Fib of 2 will call fib of 1 and fib of 0. Fib of 2 will basically call fib of 1 and fib of 0. Now, if I think one level more, what do I see? If let's say I call fib of 5. Fib of 4 will take these many operations. Fib of 4 leads to so many function calls. Now if fib of 5 comes, what do I see? Fib of 5 will call fib of 4 and fib of 3. When I say fib of 3, what will happen inside fib of 3? This entire thing that is there under fib of 3 over here, this entire thing happens over here as well. The entire thing that was present over here will come over here as well. So I'll write it over here, fib of 3. Fib of 5 will call fib of 3 and fib of 4. So what we basically see is somewhere there is a repetition of tasks that is happening. Fib of 3 is sort of getting repeated over here. This is the problem. This is the problem we notice in this particular code. That fib of 5 is calling blindly, it is calling fib of 4 and fib of 3. Fib of 4 and fib of 3 will execute. Fib of 4 will call fib of 3. And over here, this fib of 3 will also execute. So what we find is, these two things are the same thing. They will have the same answer. They will have the same processing steps, but we are not able to reduce the redundancy. We are having a lot of redundancy here. This is an overlap. This is a repetition. This is an overlap or a repetition. And what this costs you is the time complexity. Here you can see, the moment I increased, I was solving for fib 4 only. The moment I went to fib 5, so many extra function calls got added. This is an explosion of time complexity over here. However, if I say, if you are calling fib 3, and if you have got fib 3 already in the left, utilize that directly. Don't recalculate it. If I can do that utilize the information that you have fib of 3, you have calculated fib of 3 over there. Similarly, we have for fib of 2 as well. Fib of 2 also is getting calculated multiple times. 1, 2, 3. 3 times. It's a wastage of computing resources. So what we should do is, okay, we need this fib of 2. So please remember it somewhere. Utilize it. Utilize it when you need it. When you re-need it. First time when you need it, calculate it, find it out. Next time when you need it, utilize it. So over here, in this particular stack trace, we can see that, or in this particular trace, we can see that here n equal to 2 gets called. Okay, let's look over here. N equal to 1 gets called, and over here also n equal to 1 gets called. For 1, we know that it will return from the base case. But what ideally should happen is, for 1 or anything like that, especially for elements more than 1, if this fib is getting called more than once, fib of 4 is getting called more than once, we should return. We should store that value somewhere, and we should say, wherever we are again getting the request of fib of 4, directly return the value. Directly return the value that we have got. So we have to store the value somewhere and then return the value. So yes, this particular flow tells us that values will be repeated. This is a short version of that flow. And this tells us about a problem. The problem is known as overlapping subproblems. Overlapping subproblems. So, DP actually exploits two things. DP actually exploits two things. One is, first of all, optimal substructure. Optimal substructure. What is optimal substructure? This structure. This structure basically tells us that if we can solve sub-problems, if we can solve smaller problems, then very easily we can solve bigger problems. How? Simple addition. If I know fib of 3 and fib of 2, fib of 4 is just one addition away. So that is optimal substructure. I can look at this in the form of a tree where one value depends on 2, 3 values, whatever. One of those smaller values or smaller sub-problems again depends on some sub-problems. That again depends on some sub-problems. In this way, you can basically extrapolate it to the smallest sub-problems whose answers you know. So this particular thing is known as optimal substructure. The second thing that DP exploits is overlapping subproblems. Overlapping subproblems. Overlapping subproblems is what we saw over here. That okay, we are having subproblems. If some subproblem is getting repeated, DP comes in to say we can optimize this. Instead of calculating this multiple times, we can avoid the calculation and save computing resources. First time this comes, I'll calculate. Second time this comes, I'll not calculate. I'll return the value. I'll do some magic and I'll return the correct value, which is, I think, 2. Right? Fib of 3 is 2. Yeah. It will return 2 directly instead of going deep into it. That will save computing resources. Let us see how. So we can say we can store somewhere. We can keep the same memoization. Sorry, we can keep the same recursion. Yeah. So this problem actually allows us to put DP. Why? Because it has optimal substructure and it has overlapping subproblems. Now coming to the code, We can say this is a base case, this is a recursive case, we know that. Now the thing is, if we have found the answer, we can actually store the answer somewhere. So we can have the answer something like this: int dp, and initially all are -1s, all -1, all elements -1. Now the thing is, this is a dp array, each element is -1. So I can say that, okay, whenever we calculate it, fib of this plus this, we should store it in that dp array, so that next time if I get it, I will not recalculate it. So dpn is equal to fib of n minus 1 plus fib of n minus 2, and then I should return dpn. I can return dpn. What is the fun here? I can go up and say, hey, if dpn is already calculated, if dpn is greater than equal to 0, then directly return. There is nothing to see now. Return dpn. This means that it has the value already. This means that it already has the value. This thing you can also store it here, dpn equals to n. You can do that. But I mean, this is also a big O1 thing, so not needed. You can switch it below this also. It's totally up to you. I think since you are not making change for 1 and 0, it makes sense to shift this below, but both the codes will work. So I'll shift this above and keep that one below. So this is a basic implementation of a storage. It's keeping some memory. That, okay, I've calculated this, so I'll not recalculate it. Fine. Now next, after this, when I call this fib of, let's say 4, fib of 4 will call fib of 3, and fib of 2 definitely, fib of 2. Fib of 3 will call fib of 2 and fib of 1. Fib of 2 is going to call fib of 1 and fib of 0. Now if you think, fib of 1 is going to return 1, fib of 0 is going to return 0. This is your DP array. The first two I'm not going to look at, I'm not changing them, 0, 1, 2, 3, 4, 5, these are what I'm looking at. So at 2 it basically says it is 1 plus 0, it's 1 plus 0, that is 1. It will store it over here. At 2 it will store it over here, saying that my answer is 1, and then it will return that 1. The next time, okay, now fib of 3 calls fib of 1 and fib of 1 will return 1. Fib of 3 will return 1 plus 1, that is 2. So fib of 3 will store this as 2. Now fib of 4 will call fib of 2. Fib of 2 will see I already have something greater than equal to 0. It will return that. It will return what is already stored there. It will execute this code, the dp of that number which is 2 over here. dp of 2 is actually greater than equal to 0. So it will return that value which is greater than equal to 0. That comes as 1. And this guy will then add and return the value which is 2 plus 1 equal to 3. Right? Which means we have saved this part. Fib of 2 did not have to call some other things. It did not have to call some other things. We have optimized over here. This is the optimization. As it grows, you will see a larger scale optimization. If fib of 5 comes, over there you will see that fib of 3 itself returns. You don't have to go to each of them. So fib of 2 also returns directly, fib of 3 also returns directly. So much bigger optimization. So this technique works. This technique is known as memoization. We are basically using the same recursive code but with an extra storage. This is known as memoization. You can use the same tracing idea that I have shown above to understand memoization better. Now, the next part is, can we do it in a different way? There is another way. Instead of using recursion, we can say, what if we use only an array? So the idea is something like this. Hey, I know that if this is dp array 0, 1, 2, 3, 4, 5, 6, I know that DP is giving me the Fibonacci number. So since nth Fibonacci number is equal to the previous two Fibonacci numbers sum, I can say the same thing about DP. DP of n is equal to DP of n minus 1 plus DP of n minus 2. So the first two numbers definitely don't need subproblems. So I'll write those first two, that are 0 and 1. From the next one, I can say, okay, you just add the previous two elements and put it over here, you get 1. Next, you add these two elements, put it over here, you get 1 plus 1, 2. Then you add these two elements and put it over here, 1 plus 2, 3. Add these two elements, put it over here, 2 plus 3, 5. Add these two elements, put it over there, 3 plus 5, 8. And so on. This is also one way. What are we doing? We are actually going in the array from left to right, and each dpi, I am basically saying this is the sum of dpi minus 1 and dpi minus 2. That will only help me solve the problem. So I can write a simple loop saying that, okay, first I'll write that dp0 is equal to 0, dp1 is equal to 1, and then I'll write a loop something like this, that I goes from 2 up to less than n, where n is my length of the array, and I'll say dp of I is equal to the sum of the previous two elements. And since we are going from left to right, the previous elements have already been updated. So I get this dp thing. Now I'll return the last one. Okay, so we can keep less than equal to n so that we get the nth Fibonacci number 2. So this will be an n plus 1 length array. So return dpn. Here we are maintaining it in the form of an array or a table, basically a grid kind of a thing. Here we have only 1D array, you can have a 2D array. In some problems we'll actually see 2D arrays. So these are two different paradigms of solving this problem. In one paradigm I'm basically saying, okay, this is my problem, this is my big problem, and now I want to drill down and see that, okay, from the subproblems, how can I solve this? I'll go to subproblems, I'll go to their subproblems, and so on. In the second one, I'm basically saying, okay, before starting from fib of 6, think that from fib of 0, fib of 1, if I start, if I keep on adding from there, will I reach fib of 6? Yes. If I start from the left, if I keep on adding from there, at the end I'll reach fib of 6. So that is the idea, that keep on adding from the left. And in this way, at the end, you will get the sum of, the nth Fibonacci number at the right, which means you start from the smallest subproblems and you keep on working towards the bigger subproblems. So what do you see over here? You see, you started from the biggest subproblem, you reached till the smallest subproblem, and then you came back towards the original problem. Here you are saying, start from the smallest subproblem, that is I equals to 2. From there to I equal to n, I plus plus. Right? So the above technique, the previous technique, was known as memoization, and this technique is basically known as tabulation. Because the moment 2D array comes, you can only call it a table. So it's tabular DP. So recursive DP or memoization DP and tabular DP are two different forms of implementing DP. What is DP actually? DP is a technique that looks at optimal substructure and overlapping subproblems, and then it solves a problem through the subproblems by avoiding recalculation of a subproblem. So it makes the observation of overlapping subproblems, it stores the important things and avoids the recalculation. Now, before we step more into this part, memoization and tabulation, let us understand a bit that what actually classifies as DP and what does not classify as DP. Fibonacci, it classifies as DP. Fibonacci, it classifies as DP. Why? Because it follows an optimal substructure, because dpi is equal to dpi minus 1 plus dpi minus 2. This is optimal substructure, and there are overlapping subproblems. Fib of 3 reoccurred when we solved, or let's say fib of 3 only reoccurred when we solved fib of 5, right? Fib of 5. So this told us about optimal substructure, and this told us about overlapping subproblems. If I think of a different problem, like let's say factorial, is DP applicable here? Let's see. Fact of, I want to know what is the factorial of n. Okay, I want to know what is the factorial of n. So fact of n is equal to n into fact of n minus 1. So yes, if I solve this subproblem, solving this problem becomes very easy. So this is sufficient for me to say there is optimal substructure for sure. Because if I solve the smaller problem fact of n minus 1, solving fact n is very easy. Just one simple multiplication. Now the next thing is, what about overlapping subproblem? Do I have any overlapping subproblem? Let us see. Fact of 5. Fact of 5 will basically, if I write it as only f of 5 will basically call f of 4, and then it will multiply with 5. F of 4 will call f of 3. F of 3 will call f of 2. F of 2 will call f of 1. F of 1 might call f of 0. From there it will return, right? We know that fact of 0 is basically equal to 1, so from there we can return. And then as it keeps on returning, this returns 1, it will do 1 into 1, 1. 1 into 2, 2, 2 into 3, 6, 6 into 4, 24, no overlap. Each subproblem is being visited only once. And if you think about any factor, there is no overlap that happens, which means this has an optimal substructure. This does not have overlapping subproblems. So I can say no overlapping subproblems. No overlapping subproblems. So no DP. This is not a DP problem. This is not a DP problem. Or I can't use a DP solution for it. I can't have a DP formulation for it. This does not classify in DP because it does not have overlapping subproblems. You can look at the definitions, the theoretical things, and you will always find that optimal substructure, overlapping subproblems, both are necessary for it to be called a DP. If I look at another kind of example, something like longest path. Just understand logically. Let's say we have A, we have B, we have some points C, D, E, F. And then let's say I have something like this. They are connected. I want to find the distance between any 2 points, the longest distance between any 2 points. So the distance between A and B, I can say this is the longest distance. Okay, by distance I basically mean the longest distance. So let me name it as L underscore dist. Between A and B, the distance basically is from A to B along this route. 1, 2, 3, 4, 5. 5 edges are there. What about the distance from A to C? The distance from A to C is 1, 2, 3, 4. There is only 4. Now if I basically say that, okay, from A to C if I have to find, can I find it using A to B and B to C? Or let's say, I know that along A to C, definitely AF comes and FC comes. I know that from A to C when I'm going, F will come in the longest path. So can I say that L dist, the longest distance from A to C, is equal to the longest distance from A to F plus the longest distance. Longest distance means along whichever path you have the greatest number of edges. Okay, the most number of edges. From A to F, and if I say F to C, will it satisfy? Let me see. From A to C, I know the answer is 4. There are 4 edges. From A to F, longest distance means I have to take the longer problem. That is this one. I have to take this one. So A to F basically is 1, 2, 3, 4, 5. It's 5. And F to C, it's 1, 2, 3, along whichever way you go. So this is not equal, right? So what do I get over here? If I express the longest distance from A to C in terms of what comes, within them, in terms of neighbors or whatever, if I express in terms of them, I will see overlapping subproblems. Like A to C, I will find A to F. Similarly, A to D also I will find A to F. So A to F will sort of repeat. I can find overlapping subproblems. However, the main thing is wrong, which is the optimal substructure is not there. My problems don't correctly get solved by the subproblems answers. So somewhere, this also due to the lack of optimal substructure, we say there is no optimal substructure, and hence this is not DP. So for DP, you always need those two things, optimal substructure and overlapping subproblems. Okay, that's it. Now, the final aspect of the session, we will understand memoization and tabulation in a far better way. Memoization and tabulation DP. So in memoization, we basically say go in the recursive way. Fib of 4 calls fib of 3, fib of 4 calls fib of 2. This will call few things, this will call few things, this will call few things, and so on. This is basically memoization. And tabulation basically is a single array or a 2D array, whatever, and in one way you're basically from one location to another, you are shifting and you're keeping on adding the values. So from left to right, you're basically going and adding the values by simple addition. We saw how we did that, right? So yeah, this basic thing we did from left to right, and we termed this as tabulation. Now the point is, I have memoization, I have tabulation. Which is better? Let us understand the differences. In memoization, we are saying you have to solve this problem. So this is the biggest problem. We start from here. We start at the main problem. And then we go to the subproblems downwards as and when the requirement comes. But here we are starting at the over here we are starting at the smallest problems. Start at the smallest subproblems. So over here, if you see, we are going from top to down actually. We are starting from the top, gradually we are going to down, and then eventually we have to come up. But this paradigm is known as the figure suggests, we are starting from the top going to the bottom. So this is known as top-down approach. Top-down approach of DP. Memoization is basically the top-down approach of DP. Tabulation. Here, if you see 0 and 1, what are they? They are the sub-problems. They are the smallest problems. After that, you have 1 coming somewhere. Maybe over here. I mean, you have 1 coming there. You have 2 over here. You have 3 over here. You have 4 over here. So you're basically solving 0, 1 first, then going to 2, then 3, then 4, then 5, then 6, and so on. If you look in terms of this tree, we are going from the bottom to the top in that particular list, right? We are going from the left to the right, which means the smallest subproblem to the main problem. See, this is how things are represented. You have the big problem at the top. You gradually drill down to the smallest subproblem, and then you come back. That is one approach, which is memoization in this case. Now visualize the same structure. What you're doing is you're saying, I will start from the smallest subproblems. I will solve them so that I can reach the greatest problem. I have the solution ready for the greatest problem when I reach there. That particular approach hence is known as, you're going from the smallest to the largest problem, so it is known as bottom-up approach. Basically the opposite of top-down. It is known as bottom-up approach. That is, you start at the bottom and you keep on going towards the top. Bottom-up approach. We are not making a tree. We are not making a tree like this, but still conceptually you can understand that first this gets solved, then this gets solved, then this gets solved, then this gets solved, then this gets solved. So in this way the things get solved. Right, so both can be used, both will give us the right answers. We have discussed the code of both. This is our tabulation DP solution or iterative DP solution, and this is our recursive DP or memoization DP solution. Now then the question arises, what are the basic differences if I want to draw some differences between them in terms of performance, What are different? Because the answer will be the same in both the cases. Tabulation or iterative DP, and this one we also say as recursive DP. Okay, so let's see. First point, we have seen that it is top down, memoization is top down, and tabulation is bottom up. Second thing, in memoization you are calling so many things. When you are calling basically in a chain, you are calling things. Fib of 4 calls fib of 3, fib of 3 calls fib of 2, fib of 2 calls fib of 1. So somewhere there is a space toil that comes, and overall due to the function calls, you are having so many function calls. Like if you look at this diagram, you're having so many function calls, fib of 4 calls fib of 3, then fib of 2, then fib of 1. These will coexist at some point of time in your stack. So entering methods in the stack, calling functions, etc., take a bit more time. Plus, they take a bit more space due to due to storing these functions. And at the same time, it has to store so many things together. So for occupying that space, etc., there is a fractionally more time that gets consumed. So overall, memoization TP consumes slightly more time. More space as well, but I'm not writing space because it depends on what space you're using in the tabulation. If you're using an entire array in the tabulation, they are also big O n space is getting used. But here extra space is used in the stack for storing the function calls. In tabulation, there are no function calls. So here, less time. Over here, a lot of function calls, which may add burden to the space as well. And here there are no function calls, or not so many function calls. And finally, in memoization, in what order I'm calling, that is not important. I start from the biggest problem, I can call in arbitrary order. Instead of calling fib of n-1, I can first call fib of n-2, then I'll call fib of n-1. I'll add them and do. Or I can call fib of n-1 first and then fib of n-2. The order doesn't matter. Right? Each problem, it will get solved at most once. If it gets solved, the DP array stores it and it will return at the right time. So the order is not important, the order of execution is not important. That is, from where to where, the order of function calls, I can say the order of function calls is not important. However, in tabulation, the order of table or array filling is important. Array filling is important. Why so? If you visualize, if you think about that particular array, you are filling from left to right. Why? When you're reaching over here, you're saying add the previous two values and give here, which means that the previous two values need to be stored, right? For you to get your value, the previous two values have to be stored. So your order of execution should be such so that the previous two values are visited before the next value. So in every problem, you have to think, okay, which is the final answer that I want? Where are my smallest problems whose answers I already know? And then for any arbitrary subproblem, which subproblems will it depend on? You need to solve the subproblems before solving a problem. For solving any problem or any subproblem, their subproblems need to be solved. So for fib of I minus 1 and fib of I minus 2 need to be solved. The array should be filled over there. So that is the idea. So the order basically is very, very important. Right? And so memoization DP is good in terms of basically an easy coding. You just implement recursion and then you just have to apply some storage. Tabulation DP, you have to think that from where I should start. I cannot start from the end. I cannot first find out the nth Fibonacci number. I have to start from the left. So in some cases that becomes tricky from where you should start solving it. We will see a lot in these problems that we have in front of us. That why are we choosing tabulation DP, or while choosing, what are the smart choices we are making for tabulation DP to be implemented easily. So we are going to look at tabulation DP there. And there is another thing which is sometimes tabulation DP is harder to code because you don't know the order. So then you have to come back to memoization DP. So we have actually seen one problem, which is Fibonacci. Both are possible. Both are basically possible. I can use memoization DP, I can use tabulation DP. Which is better? Definitely tabulation DP will use lesser time, lesser space. Uh, and I can optimize the tabulation DP further. I can optimize the space complexity of tabulation DP further. The reason I can use tabulation is it is very easy. I can go from left to right, I can keep on solving. So it's pretty easy in that sense. I will have less function calls. So for tabulation, I can say that it will have less function calls, basically no function calls, and no space consumed in stack. Due to the function calls, etc. And then I can say easy to code. The tabulation is easy to code over here. And I can optimize the space complexity to bigger one because at any point of time I only need the previous two numbers, previous two fib values. So I can say forget the previous fib values. I don't have to remember the entire DP array. I can say, okay, when you have come to I, you need only I minus 1 and I minus 2. So possible using only 3 variables also. Possible using only 3 variables also. So the concept remains the same, but you can avoid an array, and so your space complexity drops instead of array. So the concept remains the same, that is tabulation DP. But now instead of using a table, you're saying, okay, I will use a smaller table. I'll use a smaller array of size 2 or 3, and then I'll store only the relevant 2, 3 elements. So if I take an example, something like this, you start with 0, 1, and then you get 1. Next, you basically in the array only, now you replace the first 2 elements with the last 2 elements over here, 1, 1. These are the previous 2 elements. For that you get 2. Now replace them, you get 1, 2. So now the answer basically is 3, the next number. So for each number you just need the previous 2 numbers. You don't need all the previous numbers. If I show in a different way, you can visualize in this way, that 0, 1, and then I need 1. For the next one, I don't need the previous 0, so I can forget the previous 0. And I can put a 2 over here by adding the previous 2. Next, I can forget this 1, and then 1 plus 2 basically gives me 3. Then I can forget this 1, and then 2 plus 3 gives me 5, and so on. Make sense? So this is basically, I can optimize the space there, so overall tabulation is good. It has no disadvantages. Now, there can be a different problem, like you can basically have, let's say, a problem, find in how many steps you can reduce n to 0. In each step, you can divide the number by 2 or by 3. So you are given a number n, let's say it's 10. You can divide the number by 2 or by 3. In how many different ways you can divide the number? So I can say, okay, 10, if I divide by 3, I'll get integer division. So 10 by 3 is 3. Then if I divide by 3, I will get 1. If I divide by 3, I will get a 0. This is one way. This is one way. Similarly, if I divide by 2, I get a 5. If I divide by 3, I can do something like that. So first 2, then 3, then something else, and so on. 5 by 3, basically I get 1. And then 1 by 2, I'll get 0. This is another way. This is one way. In this way, how many ways? In this way, how many ways? So if you think about it, my first step can be either division by 2 or division by 3. So first of all, if I want to look at it like a sub problem, what do I get? 10 by 2 is basically 5. 10 by 3 is basically 3. So I'm basically saying that, okay, now 5 in whatever ways that can be done. Like 5, let's say 5 can be, reached to 0 in x steps, and 3 can be reached to 0 in y steps. Then for 10, I can say, okay, I can either go to 5 first or I can go to 3 first. If I go to 5, then there are x ways. If I go to 3, then there are y ways for reaching 0. So total how many ways I have? So if I want to go to Kashmir, if I go through Delhi, I have few ways. If I go to through some other place, through some Himachal Pradesh or some place, I'll have some other ways. So if I have 3 ways there, 4 ways here, total how many ways I have to reach Kashmir? 3 plus 4, that is 7. So that is the idea. Total how many ways I have? I have x plus y, which means that if I know the answer for 5 and 3, what is x? X is actually the answer for 5. X is actually the dp of 5. And y is actually the dp for 3. If I know the answer for 5 and 3, I can just add them and get the answer. I can just add them and get my answer for 10. If I solve them completely, it will come out to something like this. If I go to 2 and to 3, so I basically get 5 and 3. 5, again 2, 3, both options possible. I get 2 and I get 1. 2, 3, 1, 1. For 2, again 2, 3, I get to 1, 0. 2, 3, 0, 0, 0, 0, 0, 0. And this one 2, 3, 0, 0. So what I'm basically saying is 2, 2, 2, 2. This is one possibility. 4 times dividing by 2. Then you will reach 0. Okay, so how many possibilities are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Number of smallest subproblems that we are reaching. You can look at it in this way. You can look at it in other way also. That okay, dp of 0 basically is 0 because, or I can say that 0 can be reached to 0 in only one way, by doing nothing. So it is basically 0. For dp1 basically is going to be, if you look at this is dp1. So dp1 basically can be expressed as dp0 plus dp0. So there are two ways for 1. One is division by 2, another is division by 3. So there are two ways. Similarly, if I know dp2, I can find out dp2 now by doing dp of 2 divided by 2 plus dp of 2 divided by 3, which is dp of 1, that is 2, plus dp of 0, that is 1, 3. So here we found that the answer is, if you see, 5 can be reached to 0 in how many ways? In 5 ways, and 3 can be reached in 4 ways. So I'll have 5, I'll have 5, I'll have 4. This is 5 plus 4 equals to 9. There are 9 ways. If I calculate in this way, what will I get? dp of 3 is equal to dp of, again, 1 plus dp of 1, which gives us 2. Sorry, 2 plus 2, 4. Similarly, in this way, I can keep on reaching. What do you see if I apply that kind of a way? If I apply tabular way, what will I get? I have to apply from the left, and I can get dp of I is basically going to be dp of I by 2 plus dp of I by 3 for all I that is greater than 0. And for I equal to 0, I can say dp of 0 is equal to 1. So this is the recurrence. Right? Now the thing is, if I solve it, if you look at basically over here, how many iterations do I need in the recursive one? In the recursive one, figure out the new subproblems basically. I have 10, 10 calls 5, 5 calls 2, 2 calls, 5 calls 1, 10 calls 3, and maybe 0. So I have only 6. I only need to solve 6 different subproblems or problems. Problems, subproblems combined. I need to solve maximum 6. I don't need to solve from 0 to 10, all the 11. I don't need to solve all of them. Recursive DP allows me to skip many in between. I don't need 9, I don't need 8, I don't need 7. But tabulation DP will force me to do that because I don't know which states are important for me. For example, if I look at a larger example, something like 50. For 50, 2 and 3, I'll basically have 25, and for 3 I'll have 16, 2 and 3. Then again 2 and 3, I'll have 12 and I'll have 8. For 2 and 3, I'll have 8 and I'll have 5. Again 2 and 3, I'll basically have 6 and 4. For this one, 2 and 3, I'll basically have 4 and 2. For this one I don't need because it's repeated. For 5, I'll have 2 and 1. And now for 6, I can say a similar thing. I'll have 3 and 2. For 4, I'll have 2 and 1. For those things, it's the same thing. No new subproblem. So if I look at it, I'm visiting 50, I'm visiting 25, I'm visiting 16, I'm visiting 12, I'm visiting 8, I'm visiting 5. 8 again, I'm not going to visit. 6, 4, 2, 3. So basically, I'm visiting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just 10 subproblems, or if you include 0, 11 subproblems. Okay, I've not included 1, and then you will have 0 as well. So very less subproblems if I look at 0. So we'll have 0 and 0 in both the cases. So my subproblems, I just have to solve for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Only for 12. Only for 12 i's, we need DP of I. However, so this is for memoization. This is for memoization. However, if I have tabulation, then I have to solve for all the 50. Then for all the 50 or 51 i's, 0 to 50, so 51. For all the 51 i's, we need DPI. So yeah. So basically here memoization is better. It will help us in saving time. I'll not go into the mathematics, but I'll leave you with one interesting hint that you see that this 8 is common over here. This 8 is common over here. So what does this tell you? That 2 and 3 and then 3 and 2 will take you to the same thing. They are two different ways. But if you change the order of the operations, they will take you to the same thing. So there's an interesting thing which a very excellent coder actually asked me at one point of time, and I had a very great discussion with him, and we reached this conclusion that the order doesn't matter, and I actually came up with a mathematical proof for that. So yeah, for that proof you can say that here memoization actually gives us far lesser time complexity, far lesser number of operations. Instead of 50, if you go to 5000, you will see far more difference. Instead of 5000, you will see far lesser number of function calls. So here we can say for this problem, due to the number of function calls or due to the number of subproblems that we are solving, for this problem, memoization is better. Memoization is better than tabulation. So there is no one liner which says that tabulation is always better or memoization is always better. It depends on a lot of factors. If you have to go by the performance, mostly it is the tabulation, so it is always preferred, and you can imagine that for tabulation you need to have greater clarity at how the control is flowing. So tabulation is often considered better, but that is not always the case. Sometimes memoization turns out to be the better. And this is one such example. Similarly, in some examples, you will see that coding the memoization thing is actually far easier than coding the tabulation thing. One other thing is you have the function calls, lot of function calls. So this can lead to Stack Overflow. First, there are ways to evade that, but this can lead to Stack Overflow as well. In Tabulation DP, you don't have that fear. All the data is in heap. It has a much larger tolerance by default. So that is one aspect of it. So yeah, in today's session, we actually learned a lot about recursion and DP. This tells us how to solve big problems in terms of small problems and how to optimally solve them. Now in the next sessions, I'll come up with on CACS problems set, I'll actually show how difficult, how some challenging problems, some really difficult problems can be solved. Some will be easy problems, how they all can be solved using this same paradigm. I will use these arguments of memoization and tabulation DP, and we will take the call, okay, here we should use memoization, here we should use tabulation. This is a DP because this is the optimal substructure, this is the overlapping subproblems. I've already shared one problem from the CACS problem set, but I think this video will give better clarity to understand the later videos on CACS problem sets. So yeah, see you all in the coming sessions. If you have any doubts about DP, about iterative DP, about memoization DP, let me know. If you have any doubts about these problems in particular, let me know in the comments. If you feel you have understood and you have liked the video, then do share with your friends who might also find the video informative. And yeah, see you all in the upcoming videos.